In this tutorial, we'll understand what logical replication is and why it's so popular. Then we'll check which are the steps to set up the replication, why we must make sure that the cluster is properly monitored, in what cases it's best to use logical replication, and finally, which are the current limitations and how we could overcome them. PostgreSQL includes a built-in, powerful and flexible feature called logical replication. It was officially released in PostgreSQL version 10 and it has been largely used since then. In many, if not most use cases, it can be considered a better alternative to physical replication in which we send bytes of data resulted from executing the SQL commands on the master server. In contrast, when using logical replication, we send the actual SQL commands. Physical data replication has some small disadvantages. First, the replica is forced to receive absolutely all the databases, tables, roles, table spaces, and so on from the original server. With physical replication, we get all or nothing. But what if we want to replicate only a single table? This is where logical replication comes into play. Here, we can choose only a subset of the tables that we want to replicate, and Postgres will replay the DML commands on the replica. Let's see shortly how it does so. First, Postgres has to decode logically the records from the WAL file and make SQL statements. Then, the SQL statements are streamed over the network to the standby server. Finally, the statements are applied to the tables in the standby server in the correct transactional order. In logical replication, we have two entities, a publisher and a subscriber. A publisher is a node that represents a certain group of tables, also called a publication. Then, to receive the changes from that particular group of tables, a subscriber can sign up by creating a subscription. Another point in favor of the logical replication is the amount of data that has to be replicated. Physical replication has to transfer every modification from the master server, even if this modification doesn't change the data itself. For example, if an index is created on a table, it's not the create index command that is sent to the standby, but instead all the modification involved in creating an index, which can be huge sometimes. This can create excessive load on the network and can become a bottleneck for a system that is under heavy load. Since in physical replication everything is transferred, we can't choose to simply run the same command on the replica. Same happens for the vacuum command. This is executed periodically and it removes the dead tuples from the tables and therefore it creates a lot of data changes which need to be transferred. Same happens for the cluster command that rearranges the rows. Although logical replication doesn't support DDL commands such as create index, we can execute it separately on the replica. We'll see later how to do this easily in practice. In this case, the amount of data sent over the network will be much smaller. Furthermore, physical data replication requires an identical configuration for the servers that are in sync. The data has to be placed at the same location on the file system. This means that we can't use this type of replication to make migrations since we can't use different versions of PostgreSQL for the master and the standby. In contrast, in logical replication, as the transfer happens at the level of SQL and not the low level of bytes, we can configure the subscriber to have different data structures. As long as the SQL commands can be executed, it will work. Therefore, we can use logical replication to perform migrations and upgrades. What's more, the data structure on the tables doesn't need to be the same. For example, we can execute an SQL command such as insert into table 1 values 1 and 2 on the master. It's not a problem when the table has more columns on the standby than A and B. The SQL statement is correct, therefore it can be executed. The extra columns will get their default values. As mentioned, when talking about logical replication, there is no master and standby. there is the publisher and the subscriber. This allows to have much more control, and we can set up multiple architectures based on our needs. For instance, we could have one subscriber that is pulling data from two machines or more, and it aggregates the data. Or we can have one publisher who is broadcasting data to more than one subscriber, each with its own set of tables. Logical replication works on the level of individual tables or subsets of tables. Also, it is possible to set up the replication for all the tables in a database. In this case, any new table will be automatically replicated. However, logical replication doesn't affect other schema objects such as sequences, indexes, or views. Let's see how logical replication works in practice. I'm going to use two PostgreSQL servers running on the same machine but on different ports. Also, each server will have its own set of directories, configurations, and its own collections of databases. Here's the sequence of steps that we'll perform. In the first phase, we set up the environment. And in the second phase, we actually set up the replication and test it. First, we're going to use the initdb command tool included in the PostgreSQL installation to create two new PostgreSQL database clusters. A database cluster is a collection of databases which are managed by a single server instance. If the command initdb is not exposed in your environment, you can find it where PSQL is installed. For this, we can use which PSQL to identify the location where PostgreSQL keeps all executables files. In my case, under user/local/bin. Here I can find the initdb executable, which can create a new PostgreSQL database cluster. First, I'm going to build a database cluster for the publisher, initdb -d, and then specify a directory where the files will be stored. It doesn't necessarily need to exist. Creating a new cluster consists in creating the directories in which the database will live, generating the system tables, and also creating the default database called Postgres. Then we build another database cluster for the subscriber, initdb -d subscription_db. Before we start the instances, both publication and subscription, we need to change some parameters in the PostgreSQL configuration file. For a minimal logical replication setup, the configuration parameter that needs to be changed is the wall level, and it should be set to logical. This instructs the server to store additional information in the wall to allow the replication, more specifically, to convert binary changes to logical ones. To edit the configuration file, I'm going to use the nano tool. So, nano, and then the full name of the file, temp/publication_db/postgresql.config. Here, I'm going to search for the wall level using Ctrl and W. Uncomment it, and then set it to logical. Also, we need to change the port that the server listens so that we could run two Postgres instances on the same machine. I will set it to 5433. To save the file, we use Ctrl and X, and then yes, and return. Then we'll do the same for the second instance. However, on the subscriber, we only change the port. We don't have to set the wall level here unless we want to make this a publisher for another subscriber down the line. Please note that for production setups, you might also want to configure the client authentication. But for this tutorial, we're going to keep it simple, so no changes here. Finally, we're going to start these two server instances. pg_ctl -d, and then we specify the directory for the publisher, and start. Indeed, we can observe that this instance was started on port 5433. And to start the subscriber, pg_ctl and the directory for the subscriber. Next, we can connect to these instances using the PSQL client. Then we specify the port and then the default database, which is Postgres. Here we can create a new database called pub. Then we switch to this database using \c and then the name of the database. Then we'll create a simple table, table1, with id int as the primary key and a column name of type varchar. And finally, we'll populate this table using generate series. Insert into table 1 values, generate series from 1 to 10, and for the other column, data concat generate series from 1 to 10. These are the entries that we just inserted into the table. Since logical replication doesn't support DDL commands, we'll have to do the same on the subscriber server. However, to transfer the same schema, we can use the pgdump command. pgdump -t table1 -s for the schema, pub, and for the current instance on the port 5433. So, this is the pgdump script that we can run on the subscriber server to have the same schema. However, instead of copy-pasting this to the other machine, we can simply pipe the result of this command as an input for PSQL to the remote machine. So the same command, we pipe the result from this to the PSQL on port 5434 on the sub-schema. Now the script have been run on the subscriber server and we can check it. \c sub to switch to the subscriber database. Then we display the tables. Of course, we could have simply created the tables here. Still, the pgdump option is best for more complicated schema tables if we also have indexes and other data structures. We see that the table doesn't have yet any row, and for that we'll have to create a publication and a subscription. Create publication mypub for the table table_1. Here, the publication is only for the table 1, but of course we can specify multiple tables or all the tables. Okay, so this is done. The last thing we have to do is to create the subscription. Create subscription mysub with connection codes dbname equals pub host equal localhost, the user, and the port is 5433. Publication mypub. Here you can mention multiple publication. Basically, one subscriber can pull changes from multiple publications. As you can see in the notice message, it started a replication slot which ensures that the cleanup for the wall should not be started until the initial snapshot is done or the delta changes are transferred to the target database. Then the wall sender started decoding the changes, and the logical replication worker has started. Then it starts the table sync. Finally, we can verify the data on the subscriber instance. As you can see, data have been replicated through the initial snapshot, but we also want to check if delta changes are replicated. Insert into table 1 values, generate series from 11 to 20, and data concatenated with generate series from 11 to 20. Select all from table 1. OK. We can also perform updates Same for the deletes. And we can also execute truncate, which will also be replicated. As mentioned, the database schema and the DDL commands are not replicated. However, as we seen in the previous example, the schema can be copied by hand using pgdump command applied only on the schema. But later schema changes need to be kept in sync manually. We know that schemas don't need to be absolutely the same on each side. However, if changes that come from the publisher don't fit into the subscribers table, then replication errors will occur until the schema is updated. In most cases, errors can be avoided if we apply the changes to the subscriber first and then to the publisher. Another limitation is that sequence data is not replicated. The columns that have been produced by the sequences will of course be replicated as part of the table. However, the sequences will start with the values from the subscriber. If a subscriber is used as a read-only database, then this shouldn't be a problem. Still, if we want to use the replica as a failover, then the sequences would need to be updated to the latest values. We can do this either by copying the current data from the publisher, perhaps using pgdump, or by setting a value that is high enough for the tables. Replication is supported only for regular tables. Starting with PostgreSQL 13, partition tables are also supported, but other types of relations, such as views or materialized views, will result in an error when trying to replicate them. As you may observe, there are some conditions which need to be met in order for the replication to work. First, the table must exist in both the publisher and the subscriber. We use the pgdump command to create the table in the subscriber. Also, for the mapping to work, the name of the table has to be the same, the column names have to be the same, and also the type. However, the column order doesn't matter. In fact, the subscriber can have more columns, or he can add columns later, or alter them. Furthermore, different types of columns are allowed, but they should at least be compatible when converted implicitly. If you're using replication, you must make sure that your cluster is properly monitored. The best way to monitor replication is to use the pgstat replication table. It contains a lot of vital information. Before we look into the table, it is important to note that the monitoring information is normally on the master. However, if you're running a cascading replication, it means that the monitoring information is also on the secondary server. Each server is only going to see the next one in the chain. So, a sending server is never going to see through a slave. In other words, in the case of cascading replication, you have to ask every sending server to get an overview. Now let's see what PostgreSQL monitors on the master server by default, considering our previous example. First, we switch to the extended view mode to see the values better. Select all from pgstat replication. One set of important metrics is the amount of replication lag measured in seconds. If we want to measure the lag in terms of time intervals, we can take a look at the columns ending with _lag. Currently, we have no lag here, but normally the delay is displayed in seconds or even minutes. If replication is in progress and working properly, then the lag is usually very small, expressed in milliseconds. There are 3 parameters, and each represents a stage in the replication process. The write lag represents the elapsed time between committed walls from the primary and the standby. In this case, the wall instructions have been sent to the operating system on the slave but not flashed yet. Then, flash lag. In addition, it considers the time to flash the changes to disk. Finally, replay lag also considers the time to apply the changes to the replica and therefore be visible to the end user. Only at this stage, the commits from the master are visible to queries on the replica. Therefore, you might want to monitor these metrics and even add alerts if a certain threshold is reached. Then, we also have the metrics that measure distance between 2 servers in terms of bytes. However, these parameters are represented in a special data type. If necessary, we can use these values to figure out how far a replica has fallen behind in terms of bytes, but for this we have to do some calculations. Furthermore, we can check what publications we have active on the server. For the publications, we can do it via the command \drp. Likewise, we can view the subscriptions using \drs. It's very important to know when to use logical replication. Otherwise, you'll not get much benefit if your use case doesn't match. So, the typical use cases for logical replication are when we need great flexibility. Logical replication doesn't require an identical schema on the 2 servers and doesn't require an identical setup of the servers in general. Because of this, logical replication can be used with different major versions of Postgres. Furthermore, it can be used to replicate between instances on different platforms, for example, from Windows to Linux. Then, the same server can work as a subscriber and publisher at the same time. Also, the same table can collect data from several servers using multiple subscriptions in order to consolidate data, for example, for analytical purposes. Furthermore, a publication can be configured to replicate only certain types of operations, for example, only inserts and updates, and ignore the deletes. Then, because logical replication offers fine-grained control, we could send incremental changes to subscribers as they occur. Also, we could fire up triggers for these individual changes as they arrive on the subscriber. Furthermore, we could give access to replicated data to different groups of users. And because it doesn't replicate changes on the physical level for operations such as vacuum and cluster, it can offer better performance when the network is low, or when there are many hops to pass to reach the destination.